Today we're going to talk about rational functions. Rational numbers are numbers that can be expressed in fraction form. So a rational function is a function that's expressed in fractional form, where the numerator and denominator are both polynomials. Let's take a look at a specific example of one. F of x is equal to 2x minus 4 over x minus 1. The first thing that we're going to do is to rewrite f of x as a quotient plus a remainder over a divisor. And we're going to use long division. X minus 1 divided into 2x minus 4. So the first step in long division is to take the first term 2x divided by the divisor's first term x, and we get a quotient of 2. 2 times the divisor is 2 times x minus 1, or 2x minus 2. Then we can change the signs of each of those terms and add, giving us a remainder of negative 2. I know it's a remainder because negative 2 is not divisible by x minus 1. So therefore, f of x expressed in quotient form is f of x is equal to the quotient 2 plus the remainder negative 2 over the divisor x minus 1. We're going to use that form later. First, before we do that, we're also going to find x and y intercepts of the graph of f of x. To do this, we're going to use the original form of the function, which was 2x minus 4 over x minus 1. Now, if you recall, an x-intercept happens when y is equal to 0. So we'll set y, or f of x, equal to 0. So 0 is equal to 2x minus 4 over x minus 1. Multiplying both sides by x minus 1, we get 0 times x minus 1 on the left, which is 0, equals 2x minus 4 on the right. That gives us 4 is equal to 2x, or x is equal to 2. So therefore, our x-intercept is the point 2, 0. Next, we're going to get a y-intercept. And the y-intercept happens when x is equal to 0. So we'll take our equation. I'm going to indicate f of x with the variable y. So y is equal to 2 times 0 minus 4 over 0 minus 1. That's going to give us negative 4 over negative 1, which is equal to positive 4. So our y-intercept is the point 0, 4. Now we're going to use both of these things to graph the function in the coordinate plane. First, I'm going to plot the x and the y-intercepts. The x-intercept is 2, the y-intercept is positive 4. And next, I'm going to look at the form of the function that we got when we used long division. F of x is equal to 2 plus negative 2 over x minus 1. Now, this looks like the reciprocal function. And if you recall, the reciprocal function is y is equal to 1 over x, and the graph of that reciprocal function looks like this, where the graph approaches both the x and the y axes and is in the first and third quadrants. So what sort of transformations do we have here? There's a plus 2 on the outside of the fraction, so that indicates that it's a y transformation, and that's going to translate our graph up 2. There's an x minus 1 where x was, so that means that x minus 1 is inside the function. That's going to indicate that our graph will move right 1. And then lastly, we have this negative 2 factor in the numerator. That means that the fraction was multiplied by negative 2. That's going to do two things. That's going to, number one, because of the negative, perform a vertical flip on the graph of the function. And then secondly, since the factor is 2, that's going to do a vertical stretch on the function by a factor of 2. Now, in order to graph this, we're just going to take into account the translations. The first asymptote, or the y-axis, gets translated right 1, and then the x-axis gets translated up 2. So these are our new axes if you want to think about it this way. Now all we have to do is put in the basic shape of the reciprocal function using the 2 points that we graphed, the x and the y-intercept. And what you'll notice about this graph is that it appears in sort of the second and fourth quadrants instead of first and third like the original parent function. The reason for this is that there was a vertical flip. So the part that was above the axis flips below the axis and vice versa. Now this is a special type of graph feature called a discontinuity. If I were to trace over the graph and I traced over the left-hand portion, I would have to lift my pencil up to graph the right-hand portion of the graph. Now we're going to look at a different type of discontinuity at x equals 1 using this next function, g of x is equal to 2x minus 2 over x minus 1. In order to graph this one, we're going to use a table of values. So I'm going to plug in a few values, -1, 0, 1, and 2. And then we'll get our y values out from that. So when x is equal to -1, the y value is 2 times -1 minus 2 over -1 minus 1. And that's going to give us -2 minus 2, or -4 on the top. And in the denominator, -1 minus 1 is -2. So that'll give us a y value of 2. When x is 0, y is 2 times 0 minus 2 over 0 minus 1. And that'll give us a -2 in the numerator and a -1 in the denominator, or a y value of 2. Next we'll plug in x equals 1. That'll give us a y value of 2 times 1 minus 2 over 1 minus 1. That'll give us 2 minus 2, or 0 on the top, 0 on the bottom. If you recall, when we divide by 0, that gives us a result that's undefined. So 0 over 0 is an undefined quantity. When x is equal to 2, we get for a y value 2 times 2 minus 2 over 2 minus 1. That's 4 minus 2, or 2 on the top, and 1 on the bottom. That gives us a y value of 2. By now, we have a suspicion that y is always 2, with one exception, and that's when x is equal to 1. So we're going to graph a horizontal line, y equals 2, but we're going to indicate that there's a point missing, or a hole in the graph, at x equals 1. Now, could we have written this function in simplified form first? Absolutely. G of x is equal to 2x minus 2 over x minus 1. We could have factored the numerator into 2 times x minus 1, and then canceled the factors in the numerator and denominator, resulting in g of x having a value of 2. Now there's something important that's missing now that we've canceled the two factors, and that is the fact that x was not allowed to be 1, or g of 1 was undefined. So we'll have to put a comment after this, or an indication of the domain. So we'll say that g of x is equal to 2, where x cannot equal 1. That's our way of indicating that there's a hole in the graph. So now we've looked at two types of discontinuities. The first type of discontinuity is called a removable discontinuity, and that's like the discontinuity that we had in example 1. We would have had to lift our pencil in order to graph with a hole in the graph. So here's an example of a graph with a removable discontinuity. The reason it's called removable is because we could simply just fill in that dot, and then we would have removed the discontinuity by plugging in the hole. The second type is a non-removable discontinuity. And a non-removable discontinuity usually indicates a vertical asymptote in the graph. We might have a couple different behaviors. near a vertical asymptote, the graph could shoot up toward the vertical asymptote and then back down from the vertical asymptote. It is also possible to have sort of opposite behaviors at a vertical asymptote. The graph could shoot down on one side and then also shoot down on the other side. Now, there are other types of discontinuities that are non-removable that are sort of combinations of these two things. For instance, we could have a vertical asymptote here where the graph is actually shooting up on one side and then has a hole in the graph at that same value on the right side. And that's sort of a combination and will result from a piecewise function. We're not going to look at that type, so we only need to concern ourselves with these two simpler types of discontinuities. All right, let's take a look at this graph. H of x is equal to x minus 4 over x squared minus 5x plus 4. First, we're going to consider the domain of h of x, and the domain of h of x can be found by factoring that denominator into x minus 4 times x minus 1. If you recall, the domain of a function involving division is that our denominator cannot equal 0. And so the factored form of the denominator x minus 4 times x minus 1 cannot equal 0. So x cannot equal 4 and x cannot equal 1 is the domain of our function. Could we have written the function in simplified form? H of x is equal to, now that we have it factored, x minus 4 over x minus 4 times x minus 1. We can cancel the common factors of x minus 4, leaving us a 1 in the numerator, and h of x will be 1 over x minus 1. Now we should also put a comment here that x cannot equal 4. The reason we have to state that is because that's indicated in the domain. The original function was not defined at x equals 4. You might notice that x is also, or h of x is not defined also when x is equal to 1. The reason that we don't have to state this is because x minus 1 is already in the denominator of the simplified version of the function, so that implies that x cannot equal 1. However, the implication that x cannot equal 4 is now gone since we canceled that factor of x minus 4. Let's try to graph this function taking into account the domain. H of x is 1 over x minus 1, where x cannot equal 4. So this is a simple transformation, right 1, or translation right 1, of the reciprocal function. The horizontal axis did not move up or down, so we will leave it where it is. Those are our two asymptotes to the graph. And then we can graph the function from there using these two anchor points. And if I were to graph the function, we're going to have a point missing when x is equal to 4. Now, in the simplified version of the function, the y value is 1 over 4 minus 1, or 1/3. So that means that we're going to have a hole in the graph at the point 4, 1/3. So we'll graph the point 4, 1/3 and indicate that there's a hole in the graph there. And then the other branch of the function does not have a hole in the graph. So that's what happens when we consider the x value that we canceled out from the function, or x equals 4. What happens at the x value that's left in the denominator, or x equals 1? There we have a vertical asymptote. And the vertical asymptote's equation is x equals 1. So to recap, There are two types of discontinuities. If the factor cancels, the graph has a hole at its critical point. To get the y-coordinate,